This is 2.6. That means I'm still trying to save you from the most dangerous topic, which is trigonometry. Are you preparing for trigonometry? Are you good with trigonometry? This will come already a little bit possibly for the first exam. So 2.6, 2.7, 2.8, 2.7, 2.8, and even 3.1 are actually going to be conglomerated into almost one lecture. I don't really see a big difference between those chapters. Okay? That's when we start derivatives. This is the last topic before derivatives. Okay? Try to do your best to prepare with trigonometry and with basic algebra, of course. All right, so there is one type of limit we are yet to consider. So here is an example. We say x is going to infinity. So x is not approaching to a number. Rather, what is x doing?
Rapidly expanding.
Rapidly expanding, and thinking of a number line, it is expanding in the direction of the right of the number line. And I'm asking then, what happens if x is growing to 1 over x? What do you think is happening?
It's decreasing, it's becoming smaller.
It becomes smaller, and can you be specific? What?
It goes to 0.
Precisely, it goes to 0. Everybody says why it's 0? Think of x as a billion. 1 over a billion is a tiny number. If x is more than a billion, 1 over it is going to be even tinier. It's like one cake divided by x amount of population, where x is huge. Now, if we're specific, this is 0 of what type? It's not ever truly 0, right? So it approaches to 0 plus, right? And if I draw the graph of it, if I draw the graph of 1 over x, so I know that if x approaches 0 plus, we go to infinity. That direction is x to 0 plus. 1 over x expands to infinity. And as I move now in this direction, the graph will descend towards 0. Now you see, if you look very far in the graph, this starts looking like the equation y equals 0, the x-axis. This is called horizontal asymptote. Now let's make it demystified. What is a horizontal asymptote? What are we really saying here? Nothing very much, except imagine you look into the clouds. And you say the cloud looks like a horse. What you're saying is that this very complicated pattern of the cloud reminds you of something more familiar. And that is a horse. Okay? So in this case, this more complicated curve, it's not a line, it's a curve, begins to remind you the horizontal line y equals 0. That's all we're saying. It's not ever truly y equals 0, because as we're approaching infinity, 1 over x is never truly equal to 0. It's always slightly more than that. But it starts looking like 0 more and more. So in other words, if I were to plot this curve on my computer, and if I were to slide to the right, the graph will eventually be indistinguishable from the horizontal number line. And if you remember our last discussion in terms of epsilon, if epsilon is 1, eventually this curve is going to dip below 1. That means that a person whose resolution is 1 pixel or with a 1 centimeter will no longer tell the curve apart from y equals 0. Eventually, for smaller epsilon, this will happen as well. Clear? So this is a horizontal asymptote. Now, what will happen if I do the limit as x goes to minus infinity of 1 over x? What are we getting? All the same 0, except if we are precise about the 0, that 0 will be now negative. So the shape of 1 over x is something like this, right? Because we're dividing by negative numbers whose absolute value, whose magnitude is very large. All right, let's try something a little bit more complicated. And this would be limit as x goes to infinity of x squared minus 1 over x squared plus 4. What happens here when x goes to infinity? And of course, try to say why.
So when the x is approaching to infinity, the number behind the x squared doesn't really matter right now. So I would say the limit is 1.
OK, good. But be careful, OK? So whatever you say, try to come up with an argument that will be very convincing that it is indeed 1 or whatever other number. So here is what we can do. You see, you are used to factor a term that appears everywhere in each of the summands. But actually, we can factor out x squared. We can factor out the largest power in the numerator. Notice it's a polynomial over a polynomial. It's a rational function. So I can factor the largest growing term in the numerator and the largest growing term of the denominator. So that looks like this. So this is x squared. What is then here? 1. Because x squared times 1 is x squared minus 1 over x squared. You see what I did? So you see that if I distribute the x squared, I get the original expression. Clear? Now, 1 over x squared is not equal to 0 because x is going to grow way past 0. So we don't really need to care about 0 there. What happens to the denominator? It's going to be what? Also x squared and 1 plus 4 over x squared. Now, at this point, I have the opportunity to cross out x squared. For any instance, no matter how large x squared is a number. So I can cross it out. Now this limit is fairly easy because this is 1 minus something that melts to 0 divided by 1 plus something that melts to 0. So the answer is that the numerator is 1 minus 0 plus divided by 1 plus 0 plus, which of course is simply 1. So this limit tends to 1. Do we have a horizontal asymptote in this case? Yes? What is the horizontal asymptote?
Straight line.
Asymptote is what? 1 what?
Just 1.
Yeah, but an asymptote is a function. So remember, when I ask you those things, always think how to simplify it. What am I really asking? When I say, is there a horizontal asymptote, I'm saying, you look at this function, whose equation is not the simplest possible. And maybe when x is very large, I can replace this equation by something much more simple. What do I replace it by? I replace it by y equal 1. So if this is y equals, so here is what happens here. If this is the y-axis, this is the x-axis, I can draw the line y equals 1. Y equals 1 means whatever x is, y doesn't care, it's just 1. So it's a horizontal line. Okay? Now, if I plug 0 into this function, it's minus 1/4. This we don't need to worry about so much. But basically, the curve, by just looking at symmetries and a bunch of other things, the actual curve that we have here will look something like this. This is y equals to x squared minus 1 over x squared plus 4. Okay? Then the dotted line is y equals 1. So when I say, yes?
Just have a quick question.
Sure.
So when you say you make it to find the y, where it touches the y, what you said, negative 1, right?
Yes, I mean, I say the other particulars of this graph, I don't want to emphasize right now, right? I mean, I'm just doing a quick, just because I know something about rational functions, I'm just plugging x equals 0, so that's how I get this point. I know a little bit about how this function behaves. But all I want from you at the moment is to know how it behaves when x is really large. When x is really large, the function, this more complicated equation, can be compared to the very simple equation. Equation is not the right word, formula, y equal 1. Right? Equation is when you're trying to relate to quantities. But this is a formula. Y equals 1. It has this graph of a horizontal line. Y equals x squared minus 1 over x squared plus 4 has this curve, more or less, as its graph. So what we're saying when we say a horizontal asymptote y equals 1, we're saying that the cloud, this function, looks like the horse, which is this line. Right? Let's see if you... I already drew this, but what happens if I take this function and I now push x towards minus infinity? So that would be x squared minus 1 over x squared plus 4. What would happen? Same exact thing. You can see it already because I drew the graph. You can do a similar analysis like I did in this example, and you see that the answer is 1. So when you're asking if there is a horizontal asymptote, what you're really doing is you're looking at your graph very far to the right or very far to the left. It's possible to have distinct asymptotes as you move right or left. Okay? In this case, it happens to be the same asymptote. Okay? Yes?
So without a graph, you can't pinpoint if there's a horizontal asymptote.
Yes, in both graphs there is a horizontal asymptote as dictated by the limit. The fact that the limit becomes, in this case, 0 means that the function really maps everything to 0 as long as that everything is a very large number. Right? So it's comparable to the horizontal line y equals 0. In this case, it's comparable to the horizontal line y equals 1. Good? So let me just give you another example where very quickly I'm just going to consider the function 1 over x squared. Okay? So this is y equal to 1 over x squared. And all I want to do is just to explain to you what is a horizontal asymptote and what is a vertical asymptote using this example. So I can easily draw this function. Let's say not so easily, but definitely you can see what happens as I approach infinity. What happens if x is very large? We already kind of did it, right? It's 0. And it's symmetric around the origin, because you see if I replace x by negative x, I get the same value of y. So it's symmetric, sorry, not with respect to the origin, rather with respect to the y-axis. So the curve looks like a volcano. Actually, a volcano with infinite, or maybe like Gabriel's horn. So this thing goes up. There is no top of the volcano, so to speak. So you can see in this graph two types of asymptotes. So if I take my screen and I focus in the center, I ask myself, this function looks like what in the center? It would look like the function x equal to 0. So that is vertical asymptote. Vertical asymptote x equals 0, because you see, as I'm looking close to the origin, my curve looks like a vertical straight line, namely y-axis, or x equals 0. Everybody understands what this word asymptote means? I'm just comparing the actual function, its actual graph, to something that I consider simple. And the simplest things I know are lines. That's why I label them for now as asymptotes. But there is actually no pressure in using only lines. I'll give you examples where the asymptote might be a parabola, because you might know how x squared looks like. Okay? It's just trying to explain the shape of something in terms of more familiar shapes. Now, if I look very far, then y equals 0 is my horizontal asymptote. Understood? So, in general, y equals f of x has a horizontal asymptote y equals to b if either limit as x goes to infinity of f of x is equal to b, or limit as x goes to minus infinity of f of x is equal to b. Y equals f of x has a vertical asymptote. X equal to a if limit as x goes to a plus of f of x is equal to plus or minus infinity, or, and you can say and or, limit as x goes to a minus of f of x is equal to plus minus infinity. So let's draw just some possible picture of what sort of asymptotes we might have. So here I drew some graph y equals f of x. What are the horizontal asymptotes and what are the vertical asymptotes, if any? Very simple question. So here you see that, well, before I tell you, write it out. What is the vertical asymptote? Ready? It is x equal to 1. Make sure that you understand why it's x equal to 1. X equal to 1 represents a vertical line. Because on a graph, you plot two coordinates. X is always 1, and y can be anything. So x is 1, y is 2. X is 1, y is 3. So you can see that you draw all the points along the vertical line 1. And you have two horizontal asymptotes. So horizontal asymptotes are y equal to 1/2 and y equal to minus 1/2 according to the picture. Now what are we really saying by vertical asymptote again? Nothing very fancy. We are only saying that if I look very close to 1, my graph looks as if it's a straight line or part of a straight line, and that straight line happens to be vertical. Okay? And if I look towards infinity, my graph starts looking like the line y equals 1/2, a horizontal line. And if I look towards minus infinity, it starts looking like minus 1/2. Let me ask you a few questions just about your intuition. But try to think about it seriously. So first question I want to ask is, can y equal f of x, the graph, so to speak, intersect or cross the horizontal asymptote? Cross a horizontal asymptote. That's my first question. Can it happen? Or do you see some difficulty with it?
No.
And if you want to answer this question, first you will tell me what is a horizontal asymptote. What are you answering? Okay? So anybody would like to try? Please?
I'm pretty sure you could cross the horizontal asymptote.
Okay.
I remember how I used to graph it, but it was like something like a parabola, not a parabola, but it would go like this. And it would still cross the asymptote. Just don't remember how to do it.
Now, okay, you say you remember that you might be able to cross a horizontal asymptote. What is a horizontal asymptote? I want you to use your logic, use your definition. So what is a horizontal asymptote? And from there try to predict if you can or can't cross it. Right? Okay, one person says you can't.
No, you can't.
You cannot, right?
No, because as you said, the value always goes near 0, but never ends. So it is going to be like,
Interesting. Interesting. Interesting.
or, I mean, if the, I mean, I think that it never crosses.
It never crosses because you see the tendency. So the curve tends towards 0. Yes, in the back?
Are we talking about this graph?
No, of course. This graph, I mean, I indicated it doesn't cross. I want to know in general, right?
Okay, so doesn't it depend on the function?
Of course it does, right? But my question is, could you find a function where the graph crosses the horizontal asymptote if one has a horizontal asymptote? You say I'm asking a theoretical question. I'm asking, No. Okay. Okay, no, no. Two people say no. Yes? Why yes?
So suppose that a function that approaches from the just say that it approaches to the right from the origin, the y value it's getting to some number, but it's not. So like the function looks like this.
Okay, I see your picture. Nice. All right. So anybody wants to say something more? Or, okay. Here is how you can reason about it. Very simply, what is a horizontal asymptote? It is something you compare the shape of your function to. That's pretty much it. When you say asymptote, it's just a simpler graph that you compare your more complicated graph to. Right? So when you say her cheeks were as round as a peach or something like that, right? When you're you're presumably speaking about a person that never saw a girl with rounded cheeks, but a person that has seen a peach. Do you understand my analogy? Right? Now, a more fatalistic analogy would be this, right? You all, or not all, but some of you watched medical shows, right? And what happens in a medical show? You see someone's, what is it called, EKG? It goes, and then it flattens. That's if it's not a good ending, right? So that is an example of a horizontal asymptote. So basically a horizontal asymptote waits for us all. But one that you are continuously crossing as long as your heart is beating. Yes? So it's possible to cross a horizontal asymptote. The answer is yes. It is possible. What function will behave a little bit like this? Again, we are not, I'm really afraid to introduce sine and cosine. I'm terrified of it. But imagine what you have is simply the function 1 over x sine of x. At infinity, it will be going to 0. That's because sine of x is only able to jump it up at most by +1 minus 1. Okay? You can use the squeeze theorem to verify that this indeed goes to 0. Okay? This crosses the horizontal asymptote, namely y equals 0, infinitely many times. Good? Yes?
So I thought that the asymptote was like kind of like a restriction point where the function can't really, reach that kind of point. So would it be like a yes or no kind of question?
Well, I mean, it's like
maybe. Definitions
maybe and whatnot, right? You can see that horizontal asymptote, based on the way I defined it, horizontal asymptote can be crossed as many times as you like. Again, what you should understand, asymptote only means comparison to something more familiar. Okay? So there is no need to even say it has to be a line. Why does it have to be a line? You might know other functions, right? And if you really have been doing mathematics for like forever, you might pick a very, very complicated function as your asymptote. It's really just comparing something less familiar to something more familiar. That's all it is. That's what you do when you're trying to describe things. Right? Her shape was like an hourglass. Presumably a person doesn't see women too often and sees hourglasses quite a lot because he sees the running of time. Okay? That's a comparison. The hourglass is, in this case, an asymptote. Correct? Now the second question, can we cross a vertical asymptote? Can a vertical asymptote be crossed? Is there any difference there? The question is enormously tricky, very, very tricky. Because I wrote something on the board, and I am now bound by what I wrote. Maybe it's not the right definition of an asymptote. What can we say now? What about a vertical asymptote? Can it be crossed?
For it to be a vertical asymptote, as the number gets larger, it is approaching infinity, so I'll say it's no.
All right. To kill the suspension? No. Or maybe yes. Actually, in the way I defined it, it can. But that's not the common definition of it, right? So you would say no. Or one would say no. Now, why would one say no is what happens when I approach? If I have a vertical asymptote, that means that as I move, let's say, as I move from the right, perhaps my curve is forced down or up this line. It's basically the curve is splattered along this line, right? It doesn't want to cross. The function is not supposed to be defined here. But notice in my definition, I only requested that the limit be plus or minus infinity, right? So based on my definition, maybe at this point, let's say 1, I define it to be 3. So maybe there is 1 point. And now I made it cross or touch. But 1 in general says no. In general, you would say, in general, it's often convention to say that the function is undefined at 1. Okay? So actually, you see, whether yes or no, I don't know. I mean, depends on what you consider. What do you consider by an asymptote? Right? One would say in general no, but I would say that that if y equals, well, if f of 1 in this case equals to 3, then yes. Yes, but at most 1 crossing, right? At most 1 intersection. Now we saw with the horizontal asymptote I can have infinitely many intersections. Here I have at most 1 intersection. How come?
It's just a property of function.
It's a property of function. A function cannot, by the vertical line test, cannot have 2 values on a vertical line. Because then it gives you 2 solutions, two outputs for the same input. Understood? All right. Let's consider a few more examples and then figure out how to deal with them in general. So what happens if I take limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. And for now, give your reasoning. Show me how you solve this. All right. So again, we're dealing with a rational function. And taking limits with rational functions is not such a difficult task. What do I do? Yes. You look at the numerator and look at the denominator. From each of them, you will factor the leading, the biggest increasing power. So x squared grows to infinity fastest. Right? If x is a million, million squared is much bigger than a million. So I factor out x squared, and in the numerator I get what? 3 minus 1 over x. Good. And then what? 2 over x squared. You all see it. Or the people that are speaking see it. What's on the bottom? Wonderful. And we did this for what purpose? We can get rid of what makes it confusing, right? Numerator is exploding to infinity. Denominator is exploding to infinity. We cannot see what it's going to. But now x squared over x squared cancels to 1. Yes?
1 over x squared.
1 over x squared. Thank you for noticing. We cross out x squared. And now we get limit where x goes to infinity, 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. What is this limit? No, it's not negative 1. Yes, it is 3 over 5. Now let's see why. This numerator is 3 minus something very small. If x is large, this number is nearly 0. And this number is even closer to 0. So it's really 3 plus or minus a number that is ignorable. And the bottom is also pretty much 0. So this, pretty much 0. So it's very similar to 0. This is very similar to 0. So the answer is that what survives is just 3 over 5. Right? So we have a horizontal asymptote y equals 3 over 5. Yes?
Just a quick question. How do you know that it's like basically 0?
How do I know it's basically 0? Well, what is 1 over a large number? It's basically 0. 2 over a large number, it's basically 0. So we have something that is almost 0 plus something that is almost 0. It's almost 0. Okay? But your question is actually going to trick a lot of people later on. Right? There's going to be a case where it's going to be slightly more complicated, where a lot of people fall into a trap. Yep.
Instead of doing all that work, can we just take the biggest?
Of course, right? You're ahead of me. Of course, we're not going to do this work. It's boring. What we're going to do, but we first are going to understand why it works, and then we're going to stop using this silly long procedure. And that's what I'm trying to do next. I call it thinking inside of the box. So what you do is observe that what ended up happening. I ended up completely ignoring, because it was limited at infinity, everything except for the leading term of the numerator and everything except for the leading term of the denominator. So I really see this as 3x squared over 5x squared, which reduces to 3 over 5. So it takes no effort to figure out this limit. Good? Let me give you one more example, and then we're going to use this box method to describe all the possible limits for rational functions. And then we're going to do it very quickly. Okay, here is another example. Now what we have is limit as x goes to infinity of x squared minus 1 over x plus 1. Figure out this limit and tell me if we have any asymptotes. All right? What do you see this limit as? Infinity. So we can just be lazy here. We see the numerator. We see the denominator. So you can say this limit is like limit as x goes to infinity x squared over x, which is the same as limit as x goes to infinity of x, which is infinity. Are there any asymptotes? Well, there is no horizontal asymptote, and there is no vertical asymptote. Actually, there is one, I'm sorry, at minus 1. Forgive me. There is a vertical asymptote, but let's consider what sort of asymptote do we have as we approach infinity. I specifically gave you this function because observe what you can do. X squared minus 1 can be written as x plus 1 over x minus 1 divided by x plus 1. This I can now cross. So now the actual limit is that this is limit as x goes to infinity of x minus 1. In other words, what this is saying, in fact, it's actually very obviously the same thing as the line y equals x minus 1. So that is called a slant asymptote. Y equal x minus 1 is slant asymptote. In other words, if I were to draw it, the graph near infinity looks like this line. Actually, it's exactly like this line at infinity. There is no distinction, right? No, this x plus 1 canceled perfectly. Okay? Let's give one more example and try to predict what is our slant asymptote, if we have one. So suppose we have this limit. When you just need to figure out what it is, this is almost effortless. What do we do?
Take the first
Right.
coefficient next to the main.
So always take not only the coefficient, but also the x power.
Yeah.
And in this case, That's just x squared. So we have 3x cubed over x squared. So this is the same as the limit where x goes to infinity of 3x cubed over x squared. The reason that happens is when you factor it out, I'm going to do it one time in general. When you factor it out, the other terms are going to be divided by some power of x. So this limit is infinity. You agree? 3x cubed over x squared is like 3x. The limit is infinity. There is going to be a slant asymptote. It's going to be similar to 3x. But to find it precisely, you just divide. So let's see what happens if I write here 3x cubed plus 5x minus 1, and I divide it by x squared minus 2x plus 7. So first of all, I need to multiply this by something to get 3x cubed. So I multiply it by 3x. So then 3x times that will be 3x cubed minus 6x squared plus 21x. Then I subtract. Now what I get is 6x squared. 5 minus 21 is going to be, it's going to be minus 18. By the way, I was not testing you. That's precisely what I'm not good at, right? I can add, subtract, multiply only abstractly, but when it actually comes to doing calculations, not my cup of tea. Right. So this is minus 18 and minus 1. Okay? Now, what you have now is 6x squared minus 18x minus 1. We need to divide by this polynomial, so we have now plus 6. So we have 6x squared minus 12x, right? And plus, yes? Sorry?
5 minus 21 is 16.
Good, you see? And you fooled me. 16. Good?
I guess it's my fault, I'm sorry.
I believed you. You see, they don't believe anybody. That's one thing that I should know.
Like you, I think.
Right? But I believed you. I figured, I mean, you are good with those things, right? I can trust you, right? So this would be 6. I multiply the 6 here. 6x squared minus 12x. And then plus what?
42.
Good, I suppose. Minus. Subtracted now. What we have is 6x squared crosses out. And we now have, what is it? It's minus 4x, right? Minus 4x and minus 43, if I'm not mistaken, correct? That's what survives after doing long division. So what it tells me is that the original function 3x cubed plus 5x minus 1 over x squared minus 2x plus 7 can be written as 3x plus 6 plus minus 4x minus 43 over x squared minus 2x plus 7. Okay? Now what it tells you is, look, do you see what's happening? Now if x is very large, this thing that I'm adding is vanishing to 0. You see, so this function looks like a line, y equals 3x plus something that disappears if x is large. Something that does not matter. You see that this is 4x over x squared, so this vanishes to 0. So it's called slant asymptote because it's just not a horizontal, it's just a slant line. So we have slant asymptote y equal to 3x plus 6. In other words, I can compare this more complicated graph to the graph that begins to look like a straight line if I look very far to infinity. If you were to plot it on your calculator, it would look like a line with slope 3. Okay? You can more or less predict this line from this limit, but not fully. You see, it's 3x plus 6. This only gives you 3x if you just look at the leading terms. Understood? So now there is nothing special about even a slant asymptote. If I change this power and made it power 4, what do you believe is the comparison function? If this were 3x to the 4 rather than 3x cubed, what would be the simple comparison function? Any ideas? X squared, 3x squared plus something. So the comparison function will be a curved asymptote. We will compare it to a parabola, provided we understand how parabolas look. Right? So you can take anything and just take any curve you believe is familiar and call it an asymptote. Okay? All right, so let's just consider the limits of rational functions very, very quickly and see all the possibilities that can happen. So let's write it as a theorem. Let r of x be a rational function, and that would be of the form a m x to the m plus a m minus 1 x to the m minus 1 all the way to some a0 divided by bn x to the n plus bn minus 1 x to the n minus 1 plus b0. So maybe for simplicity I will write it as p of x over q of x, where p and q are two polynomials. Then a, if m is bigger than n, limit as x goes to plus or minus infinity of r of x will be the same as the limit where x goes to infinity of the coefficients am x to the m over bn x to the n. In other words, I'm always only paying attention to the leading terms. They will dictate the behavior. And the limit m is bigger than n. The limit will be then what? Plus or minus infinity. Depending on those coefficients, I don't know exactly, but it will be plus or minus infinity for sure. Because this numerator is growing faster than the denominator. It has a bigger power. Okay? Like pretty much what we saw in here. Here m is 3 and n is 2. This grows much faster to infinity. So the answer will be plus minus infinity depending on the signs of a, m, and bn. B, if m is equal to n, then limit as x goes to either plus or minus infinity of rx. Anybody will take a guess what it will be? M and n are the same. What will be the answer? A over b. Am over bn will be the limit. And that would be our horizontal asymptote. So we know we have a horizontal asymptote in that case. one thing I should have actually said, plus minus. There could be two horizontal asymptotes. That's because if you cancel the x's, if x is negative, for example, it might influence the ratio to be negative or positive. So think about it. Actually, it does not have to be am over bn. Could be plus or minus. Okay, C. If m is smaller than n, limit as x goes to infinity of r of x. Anybody take a guess? Let's say actually plus or minus. So we can go to infinity or to negative infinity. What will be the answer?
Negative.
In this case, n, the denominator has a bigger power. So what's going to happen to this function? It's going to go to 0. And we will have a horizontal. There is no ambiguity. It will just go to 0. Horizontal asymptote will be y equals 0. So this is all the possibilities that can happen. I'm going to briefly sketch the proof of it. You should be able to understand why that happens, especially in concrete examples. So sketch of the proof. So really that happens because of that tedious procedure. As x goes to either plus or minus infinity of Rx, I am always able to factor out the leading term, namely x to the m. And then here we have am plus am minus 1 times 1 over x plus a0 times 1 over x to the m divided by xn bn plus bn minus 1 over x plus b0 1 over x to the n. Okay. Now can you see what's happening from there? From there, this will approach what number? Not 0, just this part, what is in brackets, approaches the number am. You see that everything else is crashed to 0. The next coefficient is crashed to 0, and every other coefficient is crashed to 0 even faster. So this approaches the leading coefficient am. This approaches the leading coefficient bn. So this limit is the same as that of am over bn x to the m over x to the n, which is just am over bn x to the m minus n. That tells you everything. Okay? Now this could be either 0, in which case you just get am over bn, or this is approaching infinity or minus infinity, and then all we care about is the sign of this thing in parentheses. It's all this quotient of leading coefficients. Okay. So this deals away with all rational functions. The next step is, of course, to look at algebraic functions, and there is a danger. So let me give you one example. Example. So let's suppose we want to calculate limit as x goes to infinity of root of 2x squared plus 1 divided by 3x minus 5. This no longer is a ratio of polynomials because we utilize the root. So it's one level up, slightly harder. Before you do any calculation, looking at it, do you feel what the number might be like? Let's actually make it a little easier. So I'll make this a 4. I prefer it. Sure. So let it be a 4. What can we do?
You can do a parentheses and the function for x to the second power plus 1 parentheses 1/2. Would that be the same thing as the square root?
What I'm worried about, I'm not sure what I heard. Did I hear distributing the roots to this part and to that part? Did I hear that by any chance?
You
No.
have the whole function inside, and then you would do 1/2. Isn't it the same thing as like?
Okay, so you want to instead of writing the root, you prefer writing the 1/2.
Yeah, I don't know if that.
Sure, I mean this is just another symbol. Maybe at some point we'll explain why you have that symbol.
I mean, if that's extra, then don't do it.
No, it's fine. Why not? I'll write it if you prefer. Why not? So let's call it 4x squared plus 1 to the power of 1/2. This expresses the same thing exactly. Okay. Root is just symbolized by power 1/2. If you're interested, I can explain later on why in office maybe. All right. First of all, any instincts? Does it feel like you might guess what the limit is?
Yeah, we can ignore the 1 and just take the square root of 4x to the second power. And it'll be just 2x and we'll go from there.
Right. So you have to be really careful. You can still use this box method, and let me explain why. Always try to, at least for a few exercises, understand why you can ignore everything else when you approach infinity. So I can look at root of 4x squared, and I can look at the leading power here. So we are going to say that this is like limit as x goes to infinity of root of 4x squared divided by 3x. And this is then limit as x goes to infinity of root of 4x squared is going to be, what is it going to be? All right, oh good, okay, 2x or negative x. So let's write it as we know it's 2, and this is a very crucial moment. Root of x squared is not necessarily x, it's the absolute value of x. So that would be 2 absolute value of x divided by 3x. But in this case, x approaches infinity, implying x is positive. So I don't have to worry about this, and I can just write limit as x goes to infinity, 2x over 3x, and I get 2 over 3. Do I have a horizontal asymptote? Or not? I got 2 over 3.
That's the asymptote.
That's the asymptote. Asymptote is just, it means that for very large values of x, if I don't do the limit, if I put a very large value of x, this more ugly expression starts just looking like y equals to 2 over 3. Right? So we have horizontal asymptote y equal 2 over 3. Now I feel that because it's a new thing, I just kind of put it in a box, and most of you are very happy about it. But I want you to understand why the box method works. Let's do it slow motion. One time. For all those examples, make sure that you can do it slow motion for at least a few of them so that you know why it works. If you're using something that you don't know how it works, you're going to make mistakes. So what I do is I take the root and I factor out x squared. So I factor out x squared. Here I have 4 plus 1 over x squared divided by, I factor out x, and I have here 3 minus 5 over x. So far, everything's good. Everything's the same. Now, very important is now I have a product of two numbers. So roots distribute through a product of two numbers. This is limit as x goes to infinity, root x squared times root 4 plus 1 over x squared over x, 3 minus 5 over x. Okay? Now, as it happens, I can cross out root of x squared and x. Be very careful. They are not always the same. I'm going to ask you another question in a moment, and we'll see if you will get it right. And then what you have is limit as x goes to infinity of root 4 plus 1 over x squared divided by 3 minus 5 over x. And now it's pretty simple to see what's happening. You see, we have 1 over x squared melts to 0. So this becomes root 4. And denominator becomes 3. So this becomes root 4 over 3, which is 2 over 3. Naturally, very tedious procedure. But make sure that in your mind you understand why that procedure was equivalent to selecting the leading term. Let me ask you another question. Very, very similar. The same question, in fact, but now limit is going to minus infinity. See what you get. Now limit is going to minus infinity of root 4x squared plus 1 over 3x minus 5. Is there any difference? Yes?
Wouldn't it be negative 2 for 3? Because if you cross, since you have it squared and the square root, you can just get rid of it, and what you have left is negative x over x.
Excellent point. So here is one algebraic trap, and almost everybody falls into it. OK, we can do this. So this limit, again, by this tedious calculation here, I hope you already begin to feel why that has to be this limit. Just the leading terms matter. So this is the same as limit where x goes to minus infinity of root 4x squared over 3x. Now, how do you simplify root of 4x squared? Yes?
4x squared to the 1/2 power, or?
Sure, but simplify means take the root.
2x.
2x, you see? You said 2x. Not quite. 2 times the absolute value of x. Very important that you see what root of, basically I'm going to write it in a moment as a separate statement. 2 times the absolute value of x rather than 2x. In this case, how do I get rid of the absolute value? What do I write instead of it? X approaches minus infinity. X is therefore a negative number. So what I write is minus 2x, because this extra negative makes this x a positive. You see, to you, you look at x as one whole thing, and it's natural for you to assume x is positive. But no, x is a placeholder. Could be a placeholder for a negative number or a placeholder for a positive number. In this case, it's a placeholder for a negative number. So now we cancel out the x, and the answer is minus 2 over 3. So we, in fact, have another asymptote. We have one asymptote which is equal to y equals to 2 over 3. And that means that if I pan my screen to the right, I will see that the graph looks like y equals 2 over 3. It looks like a horizontal line coming from the y-axis at 2 over 3. But if I pan my screen very far to the left, it will be y equals to minus 2 over 3. Before you ask, let me just show you. Root of x squared equal to absolute value of x. Put it in a box so you remember. So let me show you an example of why that must be the case. So for example, if I take root of minus 3 squared, what is my x? So in this case, x is equal to minus 3, right? But if I take this, if I apply this procedure, this will be root of 9, which will be 3, which would be the absolute value of minus 3. Do you see that to say root of x squared gives me x is to say that I can ignore this 2 and the root, and I can just whatever this value that is squared and then square rooted, I can just say that's the output. But that's not the case. The output is its absolute value. Yes?
Wait, so how did you get to absolute value x and negative 2x? I didn't understand.
OK, so this example, do you see that root of minus 3 squared is not minus 3? It's rather the absolute value of minus 3. So when I take this root of 4x squared, right? Root of 4x squared, here let me write it. Root of 4x squared is the same as root of 2x squared. Right? Now the question is the entity that I'm squaring, 2x, is it positive or negative? What do you feel? Is 2x positive or negative in this context?
Negative.
Negative. You see, because x approaches minus infinity, that presumes that we're plugging huge negative numbers instead of x. So it's negative. So what you do is just take absolute value of 2x. Before you start worrying about anything, the answer is always the absolute value. It's always the positive number. So if x is negative, the absolute value will correct it. In the first example, I didn't have to worry. I could just took absolute value. Everything goes fine. In this next example, I do have to worry. OK? Because in this next example, absolute value will multiply the number by minus 1. OK? One more example so that you don't think your life is as simple. This is just algebraic numbers, but not always are they written in such a nice form. You might have a question that looks like this. Yes?
When you take the absolute value of a negative number, even if it's negative infinity, doesn't that become positive?
If you take the absolute value of a negative number, it becomes positive.
Wouldn't the 2 times the absolute value of x be positive?
2 times the absolute value of x is positive, correct?
How come it's negative 2x on top?
Because the numerator is positive, but the denominator is negative.
Okay.
So you see, the denominator is negative. That's a good question. Right. Here is another example. And there are many of this type. You should be very wary of it. Suppose that what we have is limit as x goes to infinity of root x squared plus 1 minus x. How do we calculate this? Clearly, it's a rational function. But it's not in a nice form. It's not something divided over something else. You see, there is a conflict. It looks like infinity minus infinity. And be very careful. This symbol is very poor. this symbol is not 0, right? Because it's not a number. It just means that something explodes to infinity, something gets larger and larger and larger, and from it you subtract a number that also behaves in this qualitative way. But it can be anything. It can be infinity, minus infinity, or a number in between, depending on the rate of growth. Okay? So looking at it, you might see this growing close to very, very close to power x, right? For example, right? So this looks like the rate of growth here is the same as the rate of growth of x. That you might make the hypothesis that what you're getting is a number. But here is a safe way of working this problem. You want it to be divided by something. So what you do is multiply by the conjugate. So take this. Multiply by the conjugate and divide by the conjugate. So numerator is then x squared plus 1 minus x squared. Denominator stays as root x squared plus 1 plus x. So what we have now is limit as x goes to infinity. We have x squared minus x squared cross out. So we now have 1 over root x squared plus 1 plus x. And this number is now very easy to judge. What is this going to? 0. So the hypothesis that we made was correct. Oh, that I said. I'm rushing it a little bit. You see, this you have to be really, really careful. You see, if this were x cubed, if this were root of x cubed plus 1 minus x, what would you expect it to happen? If I replace this 2 power by a 3 power, what do you expect to happen?
Be growing larger.
Yes, to what? What would you expect the end result to be?
Infinity.
Infinity. Because then this grows much faster than this quantity. Infinitely faster than this quantity, so to speak. Understand? But here, the rate of growth is that of root of x squared, which is the same as the rate of growth of x. So we expected a number. We expected them to be cancelled out. Okay? Be very careful with those examples. Before we are over, I would like to say a few things about infinity and paradox, or the usefulness of infinity. So, first application is, let's say, when you consider physics, mechanics maybe, or mechanics. Physics. So imagine we have a piece of rope and we have astronaut A. He is pulling this rope with force F sub A. So it's happening in space. There is no gravity. We ignore that. Okay? He is pulling this piece of rope with force F of A. And here we have astronaut B. And astronaut B is pulling with force F sub B. Okay? The question is, how are the forces related? So if mass of rope is equal to 0. So the rope has no mass. How are f of A and f of B related? Any ideas? So you all played the tug of war, or maybe when you were younger, right? Where do you think the rope will go? So one is big and one is skinny. Where is the rope going to go? And yet here it's incorrect. It's not what's going to happen, right? So pick the strongest person. An elephant, doesn't matter, a buffalo. If we're in space and we're pulling this rope this way, we're going to pull the rope with the same force, always. So answer, f of A is equal to f of B always. Now, why is that going to happen? I'm going to say it in words. I'm not going to, because we're not in physics, I'm not going to go through explanations, and we still haven't covered derivatives. What's going to happen is nature does not like infinity, so it seems. By understanding that their possibilities are infinity or not infinity, nature prefers to choose not infinity. So if the forces are different, because the rope is massless, the rope will start accelerating with infinite rate in one or the other direction. So the only way out from avoiding infinite rate is to equalize the forces. So you see, if something has very little mass, even a minute force will cause a huge acceleration. So therefore, if something has 0 mass, even a minute force causes infinite acceleration. So no infinity, forces must be the same. So what will happen if you pull a rope in space that is nearly massless? What will happen is that if you're going to try to pull it with more force, you will start slipping. Your force will be, you'll be slipping, and you will not be able to hold a grip that maintains that force. You understand? You will not be able to physically cause the rope to, you would not be able to physically apply a harder force on one or the other direction. If somebody tries too hard, he's going to be slipping on it. Okay? So, and this to avoid infinity. So how it works in physics, for example, if I take 2 blocks, for example, and this is mass A, this is mass B, and I apply, basically there is a pulley here, and the pulley is massless. The pulley has, by massless means it has almost 0 mass, right? And I accelerate this pulley. What you know is that the tension in the rope, so the force applied, this force F sub B, and this force F sub A are equal, which is the tension in the rope. Because if there is a difference in those forces, that will cause infinite rotation of the pulley. You see? So this is not true if the pulley gains mass. If the pulley has significant mass, this is not true. If the pulley has very little mass, this is almost true. And if it ideally has 0 mass, it's exactly true. Okay? So by understanding infinity, you understand a possibility that cannot happen, and that allows you to solve many problems in mechanics, right? Your possibilities are either infinity or something not infinite, and nature supposedly chooses not infinity. Okay? Do you believe in infinity, by the way? How many of you believe in infinity? Raise your hand. That's nice. Sometimes the belief in infinity is related to a belief in God. Let me ask you another question. How we studied infinity in this class? Say yes if you believe we have studied it, and say no if you don't believe we studied it. No, we didn't study it. What we studied is something blowing up to without bound, right? So this symbol, which I call infinity out of poor language, poor name, right? This 8 symbol, this sideways 8, is not infinity. It's just a tendency to blow up without bound. Give me what, well, actually have enough time, I think. And if not, you'll be so mesmerized by this next example that you will not be able to leave at all. I'm going to lock the door. Okay? So we're going to now try to understand infinity a little bit, right? So this is called the urn experiment. Where is it? 2. It actually is divided into 2 parts. So I'm going to say here is going to be experiment 1. So try to understand it. I'm going to be lazy and I'm going to, well, so what you have is one mean before 12. 1 minute before 12. You're going to do the following. So first of all, in this experiment, let me just not jump the gun and explain what you have. So you have to imagine that you actually have infinitely many entities. Let's say those entities are billet balls. They are numbered 1, 2, 3. You actually have infinitely many because it's not finite, right? So for any integer, there is going to be a bigger integer written on one of the balls, okay? And you have an urn that if you want to, it can expand or it can just contain an infinite number of such balls, okay? If you don't like urn, you can imagine something else. So 1 minute before 12, you do the following. You place balls numbered 1 through 10. Through 10. And the 10th ball you immediately take out. So that's what you have 1 minute before 12. This now is 11, 12, and so on. You understand what happened 1 minute before 12? That's procedure 1. Procedure 2, 1/2 minute before 12, you're going to place the next batch of 10, and the ball whose number is 20, you're going to place out. So the picture that you will have is balls are 1 through 9, 11 through 19, 10 out, 20 out, and here you see 21, 22, and so forth. Okay? How many balls 1 minute before 12? 9. 2 minutes, 1/2 minute before 12, how many? 18. Twice times 9, right? So you notice procedure 1, 1 times 9. Procedure 2, twice times 9. Correct? Next procedure is going to happen 1/4 minutes before 12. What you're going to do at 1/4 minute before 12, you're going to place the next batch of 10 and remove out ball numbered, guess, 30. So what you have is 10 out, 20 out, 30 out. Here you have 1 through 9, 11 through 19, 21 through 29. So we have 3 times 10. Oh, 3 times 9, I'm sorry. In the urn, here we have balls numbered 31, 32, etc. are out. And you continue doing this procedure until you reach 12. So next you're going to do 1/16 before 12. You see, you're using powers of 2. So this is 1/2 to the power of 1. This is 1/2 to the power of 2. And the end procedure will be 1/2 to the power of n minus 1 minutes before 12. What you do is you insert the next batch of 10 and remove the denomination that is divisible by 10. My question is, if you understand this, how many balls in urn at 12? Cinderella time. How many equations are in this? How many balls in urn at 12? And try to give your reasoning. Well, very interesting comment. You never reach 12. How many of you agree with that? Raise your hand. But let me ask you a question. What you're doing, does the time care about what you're doing? You are busy placing those balls in the urn. So you'll place the first batch 1 minute before 12, the next batch half a minute before 12, next a quarter, next 1/8, right? Next 1/16, and etc. You are just doing this procedure, and time is indifferent to you. Right? There is a nice, in a Kojava they say, let me not give this example. If you speak Russian, I can tell you. I don't know how to translate it well, but it says, "А время торопит возница беспечный," which means time is rushed by a careless, what do you call it, careless rider. So I don't agree that we don't reach 12. Right? The time seems not to care about our activities, as you might feel. Any other answers? Yes?
So at 12, you will have carried out the procedure an infinite number of times, since you can keep it.
Right. I will have carried the procedure infinite number of times.
So the urn would have an infinite number of balls.
Okay. So you say the urn will have infinite number of balls in it, but what's your reasoning? Do you use limits or not? No. Well, that's nice. I see. I mean, by the movements of your hands, I see you're all excited to understand the end of the paradox. But don't worry, we will not leave until we understand it. Okay, so if you have to hurry, you can leave. But my advice, you're going to miss something in your life. So let's see what's happening. With each procedure, how many balls do I gain in the urn? Let's agree that that limit, as the number of procedure grows, is infinity, right? So you can say limit. Well, let me write it there. Limit as n goes to infinity of 9 times n. That's how many balls I gather, is approaching infinity. The answer to paradox 1 is indeed it's going to be infinity. But let me not just right away explain why. So let's do experiment number 2. So here is what happens in experiment number 2. 1 minute before 12, you're going to put in balls numbered 1 through 10. But instead of pulling out the 10th ball, you pull out ball number 1. How many balls are in the urn? 1 minute before 12? 9. In experiment number 2, you are going to put the next batch of 10 balls and remove ball number 2. If ball number 2 is still there, you're going to remove it. So what we have is ball number 1, ball number 2 out, 1 through 10. 11 through 20. In the third procedure, what do? You place in the next batch of 10, dig in, and remove ball number 3. So what is out is 1, 2, and 3. So this starts with 3. So with 4. How many after procedure number 3? 27. Right? 3 times 9. So we have 9 plus 9 plus 9. Okay, 27. And what happens now in experiment number 2? How many balls in the urn in experiment number 2? How many balls at 12? How many of you say infinity? Raise your hand. Nine people. The rest, I guess, they just want to go home. The answer is 0. How do I know? Notice in both cases, as I move through the steps, I accumulate more and more balls. You agree? After procedure 1, after 1 minute, I have 9. After waiting another half minute, I have another 9. So by the time I reach 12, as I'm approaching 12, more and more balls are in the urn. But let's see why is it infinity in experiment number 1. When I finish this procedure, after I have accumulated all those procedures, is ball number 1 in the urn? Yes. So you know that at least 1 ball survived. Is ball number 2 in the urn in experiment 1? Yes. Is ball number 1000 in the urn? No, because it was removed. You see, remember in experiment 1, we remove denominations that are divisible by 10. So we remove 10, 20, 30, 40, 50, 60. Those are the only ones not present in the urn. How is it different from procedure number 2, from experiment number 2, I'm sorry. In experiment number 2, I ask myself, is there anything in the urn? If so, what's the best way of checking? Just putting my arm in and digging out. Now, will I be able to pull ball number 1? No, removed in the first procedure. How about ball number 2? No, removed in the second procedure. How about ball number 1000? Removed by the 1000th procedure. So in essence, I cannot pull anything out. It's 0. You see? But in both cases, limit approaches infinity. It's not obvious that this experiment, you might think it's not easy to perform, right? Imagine what's happening in experiment number 2 especially. In experiment number 2, the universe is going to be crowded by those billiard balls. You're going to be drowning in them. And then suddenly, without any time, those balls are gone. Suddenly there is nothing. They disappear out of your existence. Now, this procedure is very difficult to perform because as you're moving balls, you're moving with a certain speed. Eventually, you will need to move them so fast that it will be faster than the speed of light. Right? So that would be prevented at least by conventional movement. So there is a limit to your speed. That's one way that in physics you try to prevent infinity from happening. Although maybe there is another way to accomplish this, not by moving.